very hot outside, no, not that hot inside yet, so we are lucky in the morning. But serverless is a hot topic on this conference. I just searched for serverless in talk titles, and I found 7 talks in this conference, minus the 3rd, and 4 to follow today. So have fun on serverless track. But my talk today is going to be a story. I'll just tell you one story of mine, and we'll see where it goes. The story starts about 6-7 years ago. Back then, I was still living in St. Petersburg, Russia. That's where I'm from. And I was a web developer, mainly on C#, .NET kind of stack, with some JavaScript, but JavaScript was not a real language yet. And one day, a friend of mine called me, and he said that he has an idea for a pet project, and he wanted me to help him with that project. My friend is an avid traveler, so he goes to different places, different cities, and he is always very careful to prepare his itinerary in advance. So he's down with his web browser, he writes down every possible place to go, like which public transport he should use, how he will get from hotel to a restaurant and stuff like that. So he makes a very detailed itinerary before going there, and he of course noticed that he spends a lot of time preparing such itinerary. So his idea for a pet project would be a web application which would somehow help people like him to prepare itineraries in advance in a more fluent way. So he wanted to start with just one city, St. Petersburg, where we both lived, because we know it very well and so on, and make a simple web application where you could like drag and drop your preferred places to visit, and then you get all the hints about public transport and how much time you'll get, how much you'll pay for what, and so on. He was mainly done with investigation and like where he gets which data, but he had no experience with web applications. So he asked, how do I do this? How do I put something out there? Of course, I asked, what exactly do you want from your hosting? Or that back then, hosting was the right word. And he said, I don't want to manage anything. I just want to write code, and then it should run somewhere. I don't want to like install updates to operating system, configure web server. I don't know what databases are. Like, give me something very simple. And of course, that's just a pet project, so I don't want to spend a lot of time. Ideally, it should be free. Most probably, nobody will use my product that is realistic. So in this case, I wanted to stay free. And if somebody does use it, I will pay a little bit. If it's popular, I will pay more. But that's my intention. The range of options back then was kind of like you could buy a shared hosting somewhere where your code runs side by side with someone else, some noisy neighbors, no guarantees. You could buy a dedicated hosting, which is expensive, so a no-go for us. And the cloud was already there. We looked at EC2, and we found them a bit too expensive and still a bit awkward back then. So actually, the thing that we ended up using was Google App Engine. First, we ended up learning some Python, because why not? And then they provided very nice developer experience. So you write a Django application, which is like a web framework for Python, and then you package it, hand it to Google, and then done. They run it for you. It's always up because it's Google. And also you get, I think you get about 20,000 requests per day for free. So you don't have to pay during development, or if nobody is using it, that's more than enough. So we developed the first version. It worked just fine. And then I moved on to other projects. I moved to the Netherlands, and I kind of forgot about this for several years. Fast forward into end of last year, this same friend called me again. He said, do you remember that project that we did? I asked her, well, yes, is it still up? He said, yes, it still works, but pretty much nobody is using it as expected. But we need to change it a little bit. I said, why? Okay, why? He said, there is one thing coming up next summer in Russia, and that's called World Cup, Football World Cup. And that means that First, a lot of people will come to Russian cities. Second, they come for football, but they have no idea about anything else, like how to spend their time otherwise, except drinking beer and stuff like that. They will compete for limited shared resources like hotels and public transport, so it's going to be hot there. And of course, there is a lot of money there, so opportunities. Actually, he ended up getting some financing from a state fund or something. I'm still not sure how that works, but a friend of his friend knows somebody, and then you get some money. That's Russian business. So he actually got already a prototype of web application, a prototype of mobile application, and he found the new services to use, to get data from. So he just needed that middle piece that we developed several years ago, make it very simple, extend it to several cities, the more the better, and pretty much done. So he asked if we can just change that service will have the look. Actually, the requirements were completely different, so we just started from scratch. And again, I asked, what are your requirements again? They were very similar. He still doesn't care about servers and operating system and so on. This time he cares more about performance because he kind of expects it's going to be used, or at least it's a probable scenario. So, but the usage is going to be very narrow during the period of the World Cup. Nobody is using it like end of last year. Nobody will use it end of next year probably. But during a couple months, it should be scaled up to a decent capacity so that everyone could use it with acceptable performance. And of course, price is still a concern. It doesn't have to be free now. Well, that would be good, but it's not realistic. But the price should scale with the load, ideally. If you have just a few users, you don't pay much. If you had like 1 million, you pay more, but then you're probably making some money out of it. So that's fine. And to me, that sounded like a perfect use case for serverless. That's how these technologies are supposed to be used. So I presented him a couple of notes like this, that function as a service is a specific flavor of serverless technology. When you write a small function in the language of choice, it does one thing well, then you define some configuration about which event would trigger this function. You package it up, you send it to your cloud provider, and then it's a problem of cloud provider to run it, to scale it as high or as low as needed, and it just works. And just to be sure that he buys this, I sent him this quote that we are living in an age of startups, billion startups like WhatsApp or whatnot. And technology is so easy now that a single person could now run a billion startup just by using serverless technology. He said, that's a cheap trick, I don't buy it. I'm not a single guy in the project anyway. But he agreed, so I guess it worked. At the time, I was mostly familiar with Azure Functions, so Microsoft flavor of Functions as a Service. So I suggested using this. Let's do it in F#, my favorite language. It's going to be cool. But he was not that convinced. I'm not sure if Azure is the best option at the moment. I've heard that AWS is the market leader. Let's compare them. Let's use them together. Okay. And because we were running all those years on Google, he had some warm feelings about Google. He said, let's also try Google Functions. They are also available. And because the only language which Google Functions support at the moment is JavaScript, so we ended up writing everything in JavaScript. So we have like a core application. It's quite simple. It's mostly calling some third-party services as needed. And then there is a layer on top which converts it to a format appropriate for AWS Lambda, Azure Function, or Google Cloud Function. A lot of people, when they talk about serverless and function as a service, they said they are concerned about vendor lock-in. In my practice, it's not a big issue if you don't So the bigger issue starts when you will use other services of that cloud, like databases and so on. But if you just use function as a service, it's very easy to convert from one provider to the other. It's not a problem. Our application looks a little bit like this. So he has a mobile app, he has a web app. Our HTTP application sits in the middle, gets the request from both. And then what it mainly does, it calls on third-party services, converts the result to what we want to show to the user, mostly throws away all unimportant stuff, and returns the response back. And as I said, my friend was very concerned about performance. He wanted to make sure that it's usable, even on spikes of load. So the rest of my talk will focus on performance of that application, and rather the tests that we were doing together. There were other challenges, but they are for a separate story. When I talk about performance, what do I care about? There are mainly two things. First is throughput, like I might get one user, I might get 1,000 users, I might get 1,000,000 users. That's the throughput, how many requests I can handle in a period of time. And the second thing is latency. So as I grow in user base, I want the response time, latency, to remain more or less constant. That's the ideal case, of course, but if it fluctuates just a little bit, that's fine. If it grows with the usage, it's not fine. Again, we made the prototype. It works, we launched it, but there was no usage yet, of course. That's a simple chart from 5 hours of usage of our applications. There is like 20 visitors there, probably ourselves and our friends and so on. So there is no load, but it's the ideal time to actually start testing, because the functionality is there. There is no pressure yet. Let's do the metrics and prepare everything for bigger usage. First, we measured if our third-party dependencies are good. Most of them were good. That's like this chart showing like sample requests to third-party dependencies. In reality, they are not that dense, but that's a reasonable assumption about the performance of those third-party services that we are using. That's good. And of course, we need to call a couple of them and then do some transformations, calculations, and so on. So we set a target at about 200 milliseconds for us for a typical response time. That's going to be instantaneous for people. And by the way, we measure like inside data center. So we don't measure the end-to-end latency from the client because they can be geographically distributed. We throw requests from the same data center and then measure how long it takes to get back. So that's the ideal case. We are not getting any users yet, but we started measuring and we got something like that. On AWS Lambda, we get some requests which are below 200 milliseconds, the yellow dots in the bottom. But lots of them are kind of slower, 400, 500, even though we are not doing anything. Okay. I looked at Google Cloud Functions. It's more or less the same picture, but the slow requests got really slower. They are above 2 seconds right now. So that's, you already feel this when you go to the application. Azure Functions, same story, same pattern here. Slow requests, fast requests, but slow requests are already sometimes 4 seconds. Okay, what's going on here? Well, it's pretty simple. The thing which is going on here is called cold start. When you just deploy your application to the cloud provider, and then you fire the first request, cloud provider actually has to do a lot of work. They go to a pool of unspecialized workers that they have available, like thousands of nodes. They pick one. That node should download your code on this node. It should start up the runtime. And then, after all this is done, then they can actually process your request and run the code. The next time the request comes, they are smart enough to keep this worker up for some time, So if it's still up, then the next request will be fast because they don't need to do this exercise again. They just reuse the same worker to process a request. So that's the fast request. But if it sits idle for some time, they don't want to waste resources on your idle application, so they will like kill this node or garbage collect it. And if your request comes in again, then the whole exercise will repeat. So on our charts, these arrows show the moments where cold start will definitely happen because it's like more than half an hour. And a typical duration of those instances, when they are kept alive, like 10 to 20 minutes. So the lesson here is simple. Serverless is not complete magic. You still need to understand something about how it works. You need to read the documents. They are quite transparent about all these procedures, and that chart is taken from one of the providers. But you still need to understand how the runtime works. And cold starts are slow, or at least slow-ish, depending on your use case. They also depend on language which you use. They depend on how many dependencies you have. If you, on JavaScript, they have lots of NPM modules and they are not bundled together, that's going to be very slow. If you're on JVM, might be slow as well because it starts. So measure first before you rely on the serverless service whether cold starts are good for you. And if not, then whether you can mitigate this issue from your application. Okay, we understood that. Next was to run the load test. How do we load test? Of course, we will use serverless to load test serverless application. That's easy. So our setup is like this. We have our application under test in the data center. It's a serverless, again, AWS Lambda or Azure Function or Google Cloud Function. Then we have a second application, which we'll call the first application, measure the duration and log it into our login metric database. It's still in the same data center, so we can reliably say that it doesn't include the routing and some random delays in internet. And then we have a scheduler which kind of produces the shape of the load that we want to simulate. For example, like we start with small, then go up, 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 then a drop or something like that. You will see examples later on. And it schedules commands to the caller application. That's actually a very nice pattern to load test any application. It doesn't have to be serverless. So if you have a cloud application that you want to test, you can apply the same pattern to simulate user load on your existing application. Actually, there are even tools to do that. One is called Serverless Auxiliary. I believe it only works for AWS Lambda, so we didn't use it. But it's just several commands in command line. What they do, they will provision AWS Lambda application behind the scenes, and will start calling as many as needed. Like you specify, I want 3 requests per second, and then it will spin up 3 instances, will call your URL. It doesn't have to be Lambda, any URL, and then we'll give you some nice statistics. So that's cool. The lesson here is very simple. Be creative with your usage scenarios. Every time you learn about function as a service, it's always based on HTTP examples, but you can be more imaginative than that. So now to the load test itself. My friend came up with a profile of users that he expects. I don't know how he did this, but he painted a chart like this. I think it's a more or less random walk. And that's like between 5 and 30 requests per second. So it's 3 to 4 orders of magnitude more than we actually had at the moment. And then we saved this shape in our file, and then we replayed this exact load on all 3 cloud providers to see how it goes. And actually, at first, the picture was like this, and it was more or less consistent between cloud providers. was quite slow most of the time, but that ended up being not a problem of function as a service, but of our third-party dependencies, because when you get only 20 users per 5 hours, it was fast, but when we started load testing it, the responses from one dependencies were consistently slow. And actually, while doing this, we violated their terms of services. We were not allowed to call them that often. So I guess they would call us or just block us after some time. The lesson here is that, again, serverless is not magic. It can be auto-scaled and very powerful, but if it depends on something which is slow, your whole application is going to be slow. Please be sure to plan this when architecting your application. Also, it's very easy, like not on purpose, to DDoS your own resources. If you have a small database somewhere, and then you start calling your AWS Lambda 5 times per second or 50 times per second, it's very easy to just crash the database. Be careful, that happens. The solution in our case was to stop calling that dependency synchronously, but kind of preload the data in advance into our own cloud database like DynamoDB or Cosmos DB, and then just load the data from those databases synchronously when a request comes in. So the schema of application looks a little bit like this. It's getting more complicated. We have extract, transform, load process. We request data periodically from third party, put them into our own database, and then when a request from the user comes in, we'll hit the DynamoDB or Cosmos DB. And that one is going to be fast because it's supposed to be used in the cloud for high load. The process looks like this. We used something called Kinesis in Amazon, basically a messaging service, large scale. We used event hubs in Azure, very comparable service. And we used PubSub in Google Cloud. It's a bit different. It's more like you publish a message and you subscribe, not an event log. But for this purpose, it's the same. So we needed to do two operations. We needed to make initial import of the data from third party, and then periodically call for updates and also load them into our database. And again, we use serverless for this. We have a function which is called serverless glue here. It's basically the same piece of code of JavaScript, but with a different configuration of event. Event is now bound to message log or event log and PubSub. Every time when a message comes to the queue, our serverless function is called. It gets the data from the queue, it puts it into our database, transformed to our format, and so on. So that's very handy. We ran a test of importing 1 million items. They are about points on the maps, doesn't really matter. We do some calculations there, so it takes time. We measured that on my laptop. It took like 4 or 5 hours to process that for 1 million. And then we thrown that 1 million into the queues of cloud providers. Google Cloud Functions did the job in 22 minutes. It's not completely correct to compare those timings between cloud providers because they are very different and there is lots of configuration and you can make one fast, the other slow. So don't really pay attention to the numbers. Don't say like Lambda or AWS is faster or Google is slower. But in our case, it was like this. So Google did it in 22 minutes, and the actual bottleneck there was the amount of invocations of cloud functions which are allowed on our account by default. Because there was no batch in there, every message was one call, it was kind of limited on that sense. I guess we could like contact Google to increase this number, but we didn't. That was fine for us. For Azure Functions, the same test took 13 minutes, but you can also see that it's very different shape. So they are kind of slowish to start scaling up, we just throw 1 million messages to Event Hub, but they still like go slow, 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 then faster, 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 faster. And the last minute, they process like quarter of the whole load, 250,000 messages. So they got really fast by the end of this exercise. But again, if you are really latency critical with these batches, it might be something to consider. Lambda did the fastest. It's like linear. It scales up immediately. The bottleneck here was actually Kinesis, so the messaging system. We provisioned, I think, 32 partitions. So Lambda spins up 32 instances. Each instance is processed in one partition, and that's as fast as it can go. There is one interesting knob there. For every AWS Lambda, you can say how much memory you provision. And although we don't need memory per se, we are not memory intensive on that test, but you can see that the processing time grows linearly with the memory. And that's actually because they also provision more CPU with the memory. So if you say, I want 1 gig of memory, they will actually give you a better hardware CPU to process your function. Again, that's documented. It's not really a surprise. But it can be confusing, like I'm provisioning memory, but it gets faster. I was surprised at first. The default seems to be 256 megabytes because 128 is kind of sluggish and not very reliable, but on this chart, it looks okay, just 2 times slower. Again, if you don't care about processing time, you just need to get the job done, maybe it's fine. But the actual money that you pay will be more or less the same for any of those scenarios because you pay per provisioned RAM times duration, and if they kind of compensate each other in this case. The lesson learned here is that serverless is not just HTTP. I actually use it most of the time not for HTTP, but for event-driven applications, message queuing, something like event sourcing, CQRS usually plays nicely with serverless applications. And of course, you need to learn how the framework that you are using works, what is the resource models, what are the knobs and options which you can tune if you really want to get high performance from it. The final story for now, it's not a World Cup yet, so the story is not ended. But a couple months ago, my friend called me again and he said, "Oh, we are going to be on TV." What do you mean? He said that there is a show on. There's going to be. Didn't happen yet. A show on TV, on Russian TV, where they discuss football and stuff, and they just going to mention this application there, like you can use it for this and this. Make a short demo, like 30 seconds or something. But then he said, we should probably expect a huge spike of users after this, because like 1 million people is watching it. Maybe they will be curious. They will not use it for real, but they'll just open the web application, go there for 5 minutes, and then close it again and never use it again, probably. But we should handle this properly. So he came up with a test like this. This very beginning of the chart was our previous test, like 30 requests per second. And then we go up, I don't know where he got this number, but up to 800 requests per second, which I compared to Stack Overflow. It's like 2/3 of Stack Overflow load. So it's not Google or Facebook yet, but it's considerable. So we ran this test on all 3 providers. I'll show them one by one. Azure Functions looks like this. So this is a response time. Percentiles. If you don't know what percentile is, basically 95 percentile means that we take the 95% of fastest requests, and then they are all bound by this number. So they are all faster or equal to this number. If 95 percentile is 300 milliseconds, then 95% of requests were processed within this time or faster. You can see that you kind of feel when the load went up, but it's still okay-ish, just 300 milliseconds. That's fine. The 99th is a little bit slower, it goes to 2 seconds, but maybe it's fine to like, for 1% of users to be a little bit slower, that's okay. Then we ran it on Lambda, and it looks like this. They just didn't feel our increase of traffic. It's just flat. The red line is 99, so there was a spike somewhere here and there, but it's like 100 milliseconds. So this looks amazing to me. Like, how do they do this? I wouldn't be able to do it with virtual machines or any kind of service that I used before. We ran it on Google Functions. At first, it looked like this, and that's a different chart. It's the amount of errors that we got. Basically, all our spike got 500 or something. But that, of course, was our fault, or at least, again, we missed one configuration. That's probably the only piece of meaningful code in my slides. But that's the change that we had to do to make it fast. Basically, yes, serverless applications are stateless, but because we know that the instances get reused between requests, they are not really stateless. You need to do things like reuse TCP connections there. And the reason why we got those error requests were actually we were out of quota for DNS or TCP. I'm not sure anymore, but because we were opening HTTP connection every time. I think the other cloud providers did it for us, these 2 lines. I'm not sure why we didn't get the problem there. But that's like a typical issue that everybody gets wrong the first time. I did it wrong in C# when I first started using Azure Functions, and like, don't create new HTTP connections just because you think that serverless applications are stateless and they disappear, and so on. And so after we did this, it started looking okay. It was all 200 fine. The response time wasn't that great, so 99th percentile is already at about 10 seconds. So I think we will not use Google Cloud Functions, but mostly because they are still in beta. I think they will improve it by the time they go live. It's still very new. The lesson here is that serverless is actually, it's not just marketing. It's very good for unpredictable, very spiky load. If you really don't know what's the load if your application is going to be, or you know it's going to be spiky, like once per month you need to generate 1,000 reports and then be quiet, that's a great technology to use. But again, know the limits. There are limits somewhere. They might be because of your incorrect implementation, but of course there are some hard limits depending on the cloud provider. Wrapping up a bit, in my abstract for the talk, I promised to give some hints where you can use this knowledge in your projects. Just a summary, the throughput is probably good enough for like 99.9 projects that you get. You can get a lot of requests from cloud services. If you are really concerned about latency, have a look at cold starts. On a normal load, they will disappear because most instances will be reused constantly. But if you really have to stay low, that might be a blocker. Other problem is that all of those services don't provide any SLA, so they don't guarantee anything. It works fine most of the time, but if it doesn't, that's kind of your problem. So be careful if you need to provide SLA to a third party or your customer. And performance is fine, but have a look at tooling, overall architecture of your application, and the price as well. I guess those factors will be more important in your decision making. The perfect scenarios for serverless for now, I would say, is prototyping. I do a lot of prototypes. All my prototypes are in Azure Functions or AWS Lambdas. Again, HTTP is fine, but if your application is event-driven, you lose a lot of messaging. That's the area where I would advise starting using serverless. Low traffic apps will usually stay within free tier, so once you prototypes, you can run it for a long time unless you get a lot of users and pay literally zero. And of course, if your profile is like the last test that we did. If you expect to be featured on TV show, welcome, use this tech. Thank you. I have 5 minutes for questions, or otherwise you can find me immediately after this talk in ground floor to discuss one-on-one.
Did you do any tests to see how long a function stays warm for before it goes cold?
I definitely did for Azure. That's 20 minutes at the moment. Lambda, I believe they changed it not that time ago, and it's something like same, like 20 minutes or so, maybe half an hour. I don't remember. For Google, no. But it looks comparable based on the rate that we get. It's same order of magnitude. They can also kill, like even if it's warm, if you just constantly do requests, sometimes they kill the instance regardless. So you can send it, and I think Amazon does this quite predictably. Once in 5 or 6 hours, they will kill it just because. No more questions, so you can grab me after the talk. Thank you.